so I'm going to do a video on section 5.4 in your textbook, polynomial functions and inequalities. There's quite a few examples in this, so I would suggest that you watch some of the video, try some questions, and then do more questions and watch more of the video. So kind of break it up for yourself. So I'm really going to start on page 276 on graphing. I'm going to do examples 2, 3, 4, and 5, which are all about graphing. If you've been having trouble with any part of these questions from your homework, hopefully I can clear up some of the questions. So in example 2, it says that they're giving you the graph of f at x is x to the fourth minus 3x cubed minus x squared plus 3x. Now the nice thing about this is in this one, they are giving you the graph. You don't actually have to come up with a graph by yourself. Now because it's an x to the fourth, that means that this will be a quartic graph. Quartic, Q-U-A-R-T, quartic. It'll be a quartic graph. And sorry, I put an extra C in there. It's quartic graph. Usually what it ends up looking like is some kind of, for lack of a better way of saying it, it looks like a wonky W. It might be nice and symmetrical and look like this, or it might not be symmetrical at all. It might look like this, something like that. But it's still like got that W shape to it. So in your textbook, the thing I like about this is they actually give you the graph. So if I try and just kind of copy them a little bit, I'm going to, it's okay. I'm going to say that each square is worth 1 here. And so here at -1, it's 0. Here at 0, it's 0. About half a square over, it's 1. And then here, it's 0. And then there, it's like -7. 1, 2, 3, 4, 5, 6, 7. And that's over 1, 2. So like here. And so it kind of looks like, oh, hold on, there was one other thing right about here. Okay, so it kind of looks like this. Oh, I need to see where that is. It's at 1, 2, 3. So my bad drawing, but there it is. It's sort of like that, okay? But then it asks you a bunch of questions. So I want to talk about what those questions are asking you. So the first thing it asks for is it asks for domain. When we're talking about domain, we're talking about x values. We're talking about looking horizontally. What I can see when I look at the x-axis, when I look across, is not only is this graph going up, but it is going slightly over, and it will continue to do so forever onto infinity because the arrow is there. And the same thing on the left side. So basically it's going to the left and the right forever. So x can be anything. There's just no restriction on what x can be. So my domain is just x belongs to the set of, that's what that funny little e is, x belongs to the set of any real number. For range, what we're looking at is we're looking at the y's. Now, if I look at the y's up and down, this graph goes up literally forever. So there's no limit on how high it can go. However, the graph does appear to have a low point. The lowest it goes is right here, which is at -7. It doesn't go any lower than that at any point in this graph. So my range is that y is greater than or equal to -7. Now, some teachers will ask you to kind of finish that statement, and say that, by the way, y belongs to the set of any real number. In other words, as long as it's bigger than -7, it can be decimals, it can be fractions, it can be positive, it can be negative, it can be anything, as long as it is greater than or equal to -7. I am basically lazy, and I let you be lazy, and I don't really care if you put that. As long as you have y is greater than or equal to -7, I know we are working within the real number system. I have had professors at university who insist upon that. So just so you're aware. The next thing they talk about is they talk about real zeros. Real zeros is just where does the graph cross the or touch the x-axis. In this case, it looks like there are 4 places where the graph crosses the x-axis. One is at -1, another one is at 0, another one is at 1, and a fourth one looks to be at 3. So my real zeros are just -1, 0, -1, 0, 1, and 3. Now, the y-intercept is where does it touch or cross the y-axis. So here's the y-axis. The graph is crossing it right here, which is at 0. So my y-intercept is just 0. I'm actually going to skip over part D because I'm going to want to talk about that a little bit more. But now they want to know any relative maximums and any relative minimums. So we need to talk about what that is. A relative maximum is a high point on the graph relative to the spots around it. Basically, how I look at it as a little mountain or a little hill, the top of a hill, because here is a relative maximum because it goes down from here on both sides. And so that is a relative maximum. They don't call it an absolute maximum because it's not the absolute highest the graph can go. The graph can actually go up forever, but relative to the spots around it, this is a high point. So because it's a point, you have to give a location. So you have to give an x value and a y value. And it looks like I'm going across about half a square and up 1 square. So my relative maximum is across 5 and up 1. So an x value of 0.5 and a y value of 1. A relative minimum I think of as a valley or a low point on the graph. So again, here is a low point because all the points around it go up from there. And here is another one. So in this case, there are actually 2 relative minimums, and you have to give me the location of both of those. This appears to be back half a square and down 1.5 squares. So back half a square and down 1.5 squares. The other one is here, which is over 2 squares and down 7. So 2 and -7. So those are your relative maximums and relative minimums. Now, the next thing they asked me about is something called symmetry. When we talk about symmetry, I'm only asking you to look at 2 types of symmetry. One is y-axis symmetry and the other one is x-axis symmetry. Meaning, if I were able, for y-axis symmetry, if I were able to cut this graph in half right along that y-axis, would the graph be the same on the left as it is on the right? And the answer for this graph is no, it wouldn't. X-axis symmetry means could I cut the graph in half along the x-axis and it would be the same on the top as it is on the bottom? And again, in this case, no, it wouldn't. So the answer is, in terms of symmetry, there is none. It has no symmetry. Okay, now I want to go back to part B a little bit because of what they ask. And it really is the thing that most people have more of a problem with. So I'm going to try and explain it as best as I can. So they want to know in part D, where is f at x greater than 0? Now I said f at x is really the same thing as y. So I could also say Where is y greater than 0? Where are your y values bigger than 0? So y values bigger than 0 are above the x-axis. So really what I'm asking is, where is the graph above the x-axis? Well, here it's above the x-axis. Here it's not. It's, whoops, let me undo that. Let me see if I can, yeah. I'll do area and I'll make it a really small area. Okay. Here it's not above the x-axis. It's not bigger than 0. The y values are like -1 and -1.5. So not here, right? Here, this little loopy-doo, that is bigger than 1. That is bigger than 0. That is above the x-axis, so it's there. Here, the y values, or the graph itself, is below the x-axis, so not here, not here. But all of this is above the x-axis. So I took it out from the picture so that you can kind of see that piece is above the x-axis, that piece is above the x-axis, and that third piece is above the x-axis. So now I have to be able to give this in terms of an answer, because here, here, and here is not really an answer. So here is -1. My x value is -1. If my x is -2, the y value is above the x-axis, or it's greater than 0. If my x is -3, same thing, still above, and so on and so on and so on. So as long as my x's are less than -1, not equal to, because they didn't say it could be equal to 0, and at -1 it's equal to 0. If they had put an equal sign underneath this, underneath the greater than or less than sign, so would I, but they didn't, so I don't. Now, the other place where it's above the x-axis is here between 0 and 1. So if my x is bigger than 0 but less than 1, the graph is above the x-axis. And finally here at 3, if x is bigger than 3, then the graph is up above the x-axis. So this would be my 3 answers to where is f at x bigger than 0. If you're hearing a puppy screaming in the background, I'm sorry, they're playing. All right, so that's example number 2. Example number 3 is a little bit yuckier, simply because they do not provide you with the graph. You have to come up with the graph. So here we go. They give us y is equal to x squared times x squared minus 4. So when you're graphing something, the first thing you really should do is you should find the real zeros. That is going to help you decide what numbers you should choose to make a table of values so you can draw this graph. All right. Now we are going to be graphing this manually without a graphing calculator. So we are really sketching this to the best of our ability, which means I'm actually going to end up with answers that are a little bit different from what they have, and I'll explain why as we go. So real zeros are wherever the graph is equal to 0. Now it is great that they gave you x squared times x squared minus 4 rather than expanding it out and saying x to the 4th minus 4x squared. Because when it's factored, it's so much easier to find the real zeros. Now, I do know that if I expanded it out, it would be an x to the 4th, meaning that this, again, is a quartic graph, and so it's going to make some kind of a wonky w. So when I'm drawing it, I know that's the shape I'm looking for. Now, there are two pieces to this graph. There is the x squared piece and there is the x squared minus 4 piece. For real zeros, the whole thing would have to equal 0. Well, if x squared is 0, then the whole thing would be 0. Or if the other piece, x squared minus 4 is 0, then the whole thing would be 0. So I'm actually going to solve those two equations. So I'm going to take the square root of this side, so I have x. So I'm going to take the square root of this side, which actually gives me plus or minus 0. But 0 doesn't typically have a sign associated with it. So when I draw it, and when I write down one of the real zeros, I'm just going to put 0 once. But because technically that's two answers, this is what's called a double root. What that means in terms of the picture is that at 0, the graph is going to do what I call bounce off of the x-axis. That's not a technical math term. That is a Mrs. Gotro way of saying it. So if you say that to another math teacher, they're going to look at you like you're crazy. But I'll explain what I mean by it will bounce. Now, the other one, x squared could equal 4, and I'm going to take the square root of both sides. But when I take the square root of 4, it could be 2 or it could be negative 2. So I actually have, it could be negative 2 or it could be 2. So it looks like I only have 3 real zeros, but I really have 4 because that one is a double root, remember. With a quartic, you should have 4 real zeros. As long as the W isn't too wonky, but they're not going to give you one like that anyway. So if I were to start drawing this, okay, if I were to start drawing this, I'm going to go here. I know that I have a real 0 at negative 2, and I know that I have another real 0 at 2, and I know I have one at 0. Now, I said there was something special about that double root. What I know is a double root means the graph is going to, and again, just my way of putting it, it's going to bounce off that. So what that means is it's not going to go through the graph like that. Once it comes up to the 0, it's going to kind of ricochet or bounce off of it and go back in the other direction. Now it could do it that way, or maybe it comes this way and bounces this way, but it's not going to cross it's not going to cross that real zeros. So great, I just screwed that up big time. Here we go. Put the lines back in, and we have a real 0 at 0. So now that I have that, I need to fill in the rest of this graph. I'm going to do that by doing a table of values. The good thing about the table of values is by finding the real zeros, I don't have to do a particularly large table of values. What I'm going to do, because these are the real zeros, this is negative 2. I'm going to pick a number before negative 2, say negative 3, because either from negative 2 the graph is going to go up or it's going to go down, and I don't know which it's going to do, so I need to figure that out. So if I take negative 3 as my thing, and I put it into the equation, so negative 3 squared would be 9, negative 3 squared would be 9, take away 4 would be 5, so I'd have 9 times 5, so I would have 45. Now clearly I'm not going to put 45 on this graph, so what I'm going to do is I'm just going to go, hey, look, it goes way up from here. That's all I'm going to do. Again, this is a sketch, not perfection. Now, in between negative 2 and 0, there is really only one whole number, and that whole number is exactly in the middle. We're going to go with just that number. Whenever you have two real zeros, pick the number, do the number for sure that is exactly in between your two real zeros. even if it ends up being a decimal, do the number that is exactly in the middle. So luckily for us in this case, what's exactly in the middle is -1. If I do -1 and I put it back up in here, -1 squared times -1 squared minus 4, you should end up with -3. So 1, 2, 3. Should end up with -3. 0, we already know is 0, so we're not going to worry about that. Now, between this real 0 and this real 0, between this one and this one, is the number 1, and that is exactly in the middle. So we're going to do 1. We're going to go back up to the equation, and we're going to do 1 squared times 1 squared minus 4. Turns out again, it's -3. Now again, we already know what 2 is. It's 0. So now we just need to pick a number bigger than 2, say 3. We put it back into the equation. 3 squared times 3 squared minus 4 turns out to be 45. So when I play connect the dots here, this comes down, this comes up, this goes down, this comes up. This is what we have, and it basically is a W, right? Okay, now in the textbook, they actually choose to do -1.5, which actually goes lower than this y value of -3. I would never choose to do -1.5 as a guess unless -1.5 was directly in the middle. So they have a different answer. They go a little lower than we do, but I would totally accept this as your answer. All right, so now that you have the graph drawn, they ask you some questions that they want you to answer. So first off, they ask for the domain. The domain is that x is any real number. Goes to the left, goes to the right forever. The range, and this is where I'm going to have a different answer from the textbook, because the textbook assumes you had a graphing calculator which did all this fancy math for you. We didn't. We did a table of values. We did not put in our table of values -1.5 because there's no reason to go there. Like there's just no reason to pick -1.5. So what it looks like from our logical graph is that the lowest this goes is -3, and the graph goes up from there. So my range would be that y is greater than or equal to -3. And even though that's not the answer they have in the textbook, I am okay with that. Any zeros? Well, we already figured that out at the beginning when we were starting to graph it. So we really already had that answer. A y-intercept, well, that would be right here at 0. And then finally, describe any symmetry. Well, what about y-axis symmetry? If I cut it in half, is it the same on the left as it is on the right? Turns out in this case, yes, it is. So it has y-axis symmetry. That's what they're looking for in example 3. Example number 4. If I can erase all this. Example number 4, again, very nicely gives this to us factored. They give us f at x is equal to x plus 4, x plus 1, and x minus 1. And the first thing it asks us to do is graph it. When I'm going to graph it, thankfully it's in factored form. It's already in its pieces. So I'm actually going to find the real zeros first. Even if they don't ask for it, I'm going to find that because it's going to help me graph it. The real zeros are whatever will make each of these brackets 0. So -4 would make that first bracket 0. -1 would make that second bracket 0, and 1 would make that third bracket 0. Now, if I were to multiply this out, I would end up with x times x times x for part of it, which would be an x cubed graph. So I know this is a cubic function. So I know that the graph in some way should look like this. Any cubic graph is going to have that kind of wave to it. So when I graph it, I know I should get that in some way. It might be a little bit steeper than that. It might not be as steep as that, but I should get that in one way or another. So if I'm going to graph this here and here, I know I have real zeros at -4. So 1, 2, 3, 4. I know I have real zeros at -1. And I know I have real zeros at 1. So -4, -1, and 1. So now I need to come up with a table of values. So x and y. Now when I'm choosing what I'm going to do, I know I'm going to pick a number before -4. So say -5. And I'll put that back up in here. -5 plus 4 is -1. -5 plus 1 is -4. And -5 minus 1 is -6. And when I multiply that all out, I get -24. So again, I'm not going to put that on my graph. There's not enough space. But I'm just going to go, hey, it goes way down there somewhere. Now, at -4, it's already 0. No need to figure that out. Now, to figure out what I should do here, halfway in between -4 and -1 is actually negative. Let me see. There's 1, 2, 3 squares. So I would go back 1.5. So that's actually -2.5. So I'm going to make sure I do -2.5 on my graph. But I'm also going to do the even numbers as well. So I'm going to do -3. I'm going to do -2.5. And I'm going to do -2. When I put -3 back up into here and I work it out, I actually get 8. So at -3, it's 8. Now I don't have enough space. I'm going to count each square going up as 2. So this would be 2, 4, 6, 8. So this would be up here. It's just because I don't have enough space. And then I would do -2.5 because a lot of times the middle will be the high point or the low point. Now it turns out in this one it's not. I'm not going to sit and figure it out. You can figure it out, but it turns out it is slightly lower. I think it works out to be like -7.75 or something, but it turns out at -2.5 it is slightly lower. And then I'm going to do, you can figure that out up here. I'm going to put -2 in, which would give me 6. So at -2, it's 6, 2, 4, 6. It's right here. And so I can tell you that this is coming up and then coming back down. Now in between -1 and 1, I need to figure out what's going on. The very middle is 0. So I'm just going to do 0. So if I do 0, this would be 4 times 1, which is 4, times -1, which is -4. So again, each square vertically is going to be worth 2, so 2, 4, right here. So I know it's going to come down and back up, and then I would pick a number bigger than 1, say 2. I would put that up for my x, and I would get 18. Again, not really space on here for that, so I'm just going to say, hey, it heads up. So I've got that wonky wave thing happening. So now they just want me, again, to answer some questions about this. So the first thing they asked me for is the real zeros. Well, handily enough, I already did that. Then they want the domain and the range. So, the domain is really x is any real number. It's a really bad E. Is any real number because it's going to the left and the right forever. And then the range, well, if we look, it's going down forever on that side. It's going up forever on that side. So really, y is any real number as well. Could be anything. The y-intercept. The y-intercept is actually down here at -4. It's crossing the y-axis at -4. Now they want to know the intervals where f at x, meaning the y values, are less than or equal to 0. In other words, below the x-axis. So I'm just going to do this in a different color so that you can see. So where is it below the x-axis? It is below the x-axis all here. That's below. It is also below the x-axis here. So where is here? That is the question. So when we talk about that, it is if my x is less than or equal to this time, because they have an equal sign, x is less than or equal to -4, or if x is between -1 and 1. So if x is bigger than or equal to -1, but less than or equal to 1. So that's my answer for that. Then they ask me, is there any symmetry? So again, I look at that y-axis, I look at that x-axis, and I go, no, not really, no symmetry. And then they ask for something called end behavior. I'll put that over here just because of space. I am not looking for anything fancy to my answer for end behavior. I want you to look at the left side and I want you to look at the right side and give me an answer. So if I look at the left side, the end of the graph at the left side, it ends by going down infinitely, forever. So you could answer that in a bunch of different ways. And again, I'm not really picky. You could say they get more and more negative. They go down. I tend to, because I'm lazy, I write it this way. The left is negative infinity, meaning it goes negative. It goes down forever. And that way I don't even have to write any words. On the right side, it goes up forever, or the numbers continue to get more positive, they get bigger, it doesn't really matter. I write it as positive infinity. Again, basically just because of laziness. Okay. Example 5 just talks about a double root again, which I already went over in example number 3, what a double root is. So I'm going to skip example number 5. Okay. And I'm going to talk about example number 6 and example number 7, and then we're finally going to be done talking about this section. It takes forever. These sections in chapter 5 are huge. Okay. So, example 6 and 7 deal with inequalities. Basically, when there is a greater than or less than sign. And they just want to know in this, what values of x could I put in there and make it so that when I put x in there, it works out being smaller than or equal to 6. Well, the first thing you should do is you should move everything over to one side and make one side 0. So simply move the 6 over and have less than 0. Now, there's a couple of options open to you. However, one of them I would not choose. Because if you look in the textbook on page 279, solution 2 is to solve it graphically. So basically, draw the graph and figure out where is the graph less than 0, meaning below the x-axis. So just to give you sort of insight into what they're talking about, this is a quadratic. The highest exponent is a 2. We know, because we're smart people, we know that a quadratic means that if I were to graph this, that this would be a parabola. Now, I don't really know what that parabola is going to look like because I'm not doing a table of values or anything like that. But let's just say it does this. What you are actually looking for is you are looking for where is the graph less than 0, so below the x-axis. So it would be from here to here. And what you would have to figure out is where is here and where is here. So you could do it by graphing. However, especially if it's not just a quadratic, if it's a cubic or, heaven forbid, a quartic. Graphing it and trying to find the real zeros, if it is not already factored for you, is going to be a pain, and you're not going to want to do it. So let me show you a different way to solve it that does not require you to graph the graph of that equation, because I don't know about you, but I don't want to. So this involves still finding the real zeros, but instead of calling them real zeros, now they're going to call them critical numbers. Critical numbers, real zeros, mean exactly the same thing. It's just because we're not graphing it, we're not calling it a real zero, because a real zero means where's it touching or crossing the x-axis. Well, we're not going to graph it, so we're not talking about where it's crossing the x-axis. So instead of calling it a real zero, they call it a critical number, but it means the same thing. So don't let the language mess you up. Now, this is a quadratic function. If I wanted to solve a quadratic function, way back at the beginning of chapter 4, we actually talked about 5 ways to do that. One of them was to graph it, but we said we don't want to do that. Another way was to complete the square. I don't know about you, but I don't want to complete the square. But 2 other ways were factoring, or using the quadratic formula, that negative b plus or minus the square root of b squared minus 4ac all over 2a. It's your choice. For me, if I see x squared plus x minus 6, I can factor that in my head fairly quickly, so I would. And I would go, that would be x plus 3, and x minus 2 is less than 0. Meaning that my critical numbers would be negative 3 and 2, because that is what would make those brackets 0. Now, if you had done the quadratic formula, your x would have turned out to be negative 3 and 2. It would have ended up being those critical numbers. All right, now, what do I mean when I talk about critical numbers instead of calling it real zeros? Why the change in language? Because rather than look at it as a graph of a parabola, we're going to talk about a number line. And on that number line, and I don't care if it's accurate or not, let's say negative 3 is back here and 2 is here. I don't care if it coordinates to the spaces, doesn't really matter. So I have negative 3 here and 2 here. What this does is it breaks this line up into 3 sections. The section before negative 3, the section between negative 3 and 2, and the section after 2. So there's really 3 sections there. Now again, sections is not a fancy enough math term. And so rather than call them sections, they call them test intervals, which sounds terrible, but it's really not. All it means is if we're going to choose a number in each of those sections that would fall in each of those sections, and we're going to test it, we're going to put it back into the original equation or the one I factored, and we're going to see if it makes the math sentence true. If one number in that test interval or that section is true, then all the numbers in that section are true. So we're going to pick a number in this first section, first. So numbers before negative 3. You can pick any number you want that is before negative 3. You can pick negative 4. You can pick negative 5. You can pick negative 672. It doesn't matter. You can pick anything as long as it's before negative 3. I'm going to go the easy route, and I'm going to pick negative 4. I'm going to put that back into either x squared plus x minus 6 or into x plus 3 times x minus 2, either the factored or non-factored form, doesn't matter. So if I do negative 4 plus 3, that's negative 1. And if I do negative 4 minus 2, that's negative 6. And so when I multiply -1 times -6, I get 6 is less than 0. And I look at that and I ask myself, is that a true statement? And no, it's not. So numbers in this section or in this test interval don't make that math sentence true. So that section is a no. Like the numbers don't work. They don't work out to be less than 0. Okay. So now I'm going to go to the next section or the next test interval, and I'm going to pick a number, any number I want, as long as it's between -3 and 2. Now, if I have the opportunity to pick the number 0, I very often am going to pick the number 0 because it tends to be easiest to do. You don't have to pick 0. If you would like to pick -1.739, go ahead. But that's crazy. I'm going to pick 0. 0 plus 3 is 3. And 0 minus 2 is -2 is less than 0. 3 times -2 is -6 is less than 0. And I go, well, is that true? And I go, yeah, it is. Since that's true, that number is in this test interval, this section, this middle section here. If one number in that section works, all of the numbers in that section work. So all of these numbers work. Now think about graphing on a number line. If there is no equal sign here, we put an open circle at -3, and we put an open circle at 2. If there was an equal sign here, then I would have colored in those spots, but there wasn't. So now I have my last section to test, which is bigger than 2. And again, any number you want, as long as it's bigger than 2. So I'm going to pick 3. 3 plus 3 is 6. 3 plus 3 is 6, and 3 minus 2 is 1. And so I end up with 6 is less than 0, which it is not, so that section doesn't work either. Now you don't have to put X's there. I'm just doing that for your visual. So if you were to give this answer in number line form, you would literally just leave it like this. Open circle at -3, open circle at 2, and colored in between. That's it. You can also give this as a math sentence if you want. And I don't care if you do or not. You can either leave it on as graphed on drawn on a number line, or you can make a math sentence. And so the math sentence would be that X has to be greater than -3 but less than 2. If X is bigger than -3 but less than 2, then this math sentence right here will work out to be less than 0. And that's it. One more example. I've been talking for almost 45 minutes straight. I'm going to need a lot of water when I'm done. So the next one is the same idea, except this time it's not a nice, easy quadratic equation. They give us this time x cubed plus 3x squared minus x minus 3 is greater than or equal to 0. So again, if you wanted to solve this graphically, they have that in the textbook. If you wanted to solve it graphically, you'd have to do like a big table of values. You'd have to probably factor it, find real zeros. I know it's a cubic function, so I know it's sort of going to look like this. And what they're asking for is, where is it greater than or equal to 0? Where is it above the x-axis? So there and there. But you'd have to tell me where there and there were. But again, we're trying to get away from this having to graph it all the time thing. So we still need to find the real zeros or the critical numbers. Always, 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 you're going to find that first. So we have to think back again to the last half of chapter 4, where we factored horrible polynomials like this. So what did we do? Okay, what we did, remember, think back. There's no number in front of my x cubed. That's good. So I'm going to take the number 3 and I'm going to say, what are all the factors of 3? Well, plus or minus 1 and plus or minus 3. I'm going to try each of those until I find one that when I replace it into my equation actually equals 0. So the good news is 1 actually does that. 1 cubed is 1. 1 squared is 1 times 3 is 3. So 1 plus 3 is 4. Minus 1 is 3. Minus 3 is 0. So if x is 1, then we have, that's a critical number or a real 0. Now I need to figure out, are there other critical numbers or real zeros? So remember what we did synthetic division. So again, in case you forget what synthetic division is, we put the number out here and we take the coefficients in front. So in front of the x cubed is 1, in front of the x squared is 3, in front of the x is -1, and the constant is -3. So refresher on synthetic division. Take the first number and just move it down. Then take this one and multiply it with this one, which gives you 1. Then we add these two numbers together, which gives me 4. Now take this one and multiply it by 4, which gives me 4, and add these, which gives me 3. Then 1 times 3 is 3, and this gives me 0. You always want that to be 0 because that is your remainder, and this is x squared and 4x and 3. Now, you can either try and factor that, or you can do the quadratic formula with that, but you need to figure out what the other critical numbers or real zeros are. If I was to factor that, that would be x plus 3 and x plus 1, meaning that -3 would be a real 0 or a critical number, and so would -1. So now those are going to make up my test intervals. So again, thinking about a number line, we're going to have -3, we're going to have -1, and we're going to have 1. So it actually breaks it up this time into 4 test intervals or 4 sections. I have the section before -3. I have the section between -3 and -1. I have the section between -1 and 1, and then I have the section after 1. So I really have 4 different test intervals there. Now that's too much writing. It's too confusing. So here we go. And again, I don't care if you count out squares. This can be -3, this can be -1, this can be 1. Doesn't matter. As long as they're in the right order. So I need to pick a number less than -3. Anything at all does not matter. I'm going to pick -4. And I'm going to take that and I am going to put that, I need space here. I'm going to put that back into my equation. So -4 cubed is -64. -4 squared is 16. 16 times 3, I don't remember. 16 times 3, that's 8. 48. Minus -4, so really +4 minus 3 is greater than or equal to 0. So -64 plus 48 is what, like 16, sorry, that's 16. And 16, it's -16. -16 plus 4 is -12, and -12 minus 3 is -15, is greater than or equal to 0. And so is that a true statement? Well, no, it's not. So this section, anything before -3, does not work. So you don't have to put the x there. Again, I'm just doing that because all you're hearing is my voice. So I'm just doing something visual for you. So now I need to pick a number between -3 and -1 because that is my next test interval. Any number you want between -3 and -1. There's lots of them, but I would pick -2 because it's the only whole number. I mean, you could pick -1.73 if you want, but that seems like a lot of work for no reason. So I'm going to pick -2. Negative 2 cubed is negative 8. Negative 2 squared is 4. 4 times 3 is 12. Minus negative 2, so really plus 2, minus 3. So negative 8 plus 12 is 4. 4 plus 2 is 6. 6 take away 3 is 3 is greater than or equal to 0. Well, yes, it is. So this test interval works. So yes, 2 in here. Actually, let's do that in red so that you can see it. So yes, 2 in here. Now, do I color in circles? Do I not color in circles? Well, there's an equal sign here, so I do. I color in this end and I color in this end. Now I need to check about the next test interval, which is between -1 and 1. You can pick any number you want between -1 and 1. Again, if I have a chance to choose 0, I'm going to pick it, and I can. So 0 cubed is 0. 3 times 0 is 0, minus 0, minus 3, so I end up with negative 3 is greater than or equal to 0. No, it's not. So that section doesn't really work. So it's a no. And then finally, finally, I have to look at the last section, which is numbers bigger than 1. Again, any number you want. You can pick 2, you can pick 3, you can pick 657,000. Doesn't matter. Just needs to be bigger than 1. So I'm going to pick 2. 2 cubed is 8. 2 squared is 4 times 3 is 12 minus, what am I doing, 2? Minus 3. So 8 plus 12 is 20. Take away 2 is 18. Take away 3 is 15 is greater than or equal to 0, which, hey, yes, it is. So it can go on to infinity because this section doesn't really have an end to it. So I just put an arrow saying it can go forever and close dot here. So you can leave your answer right like that on the number line, or you can make it a math statement. That math statement would be that x can be greater than or equal to -3, but less than or equal to -1, or x could be greater than or equal to 1. So I don't really care whether you leave your answer as a number line or whether you leave your answer as a math statement. It doesn't make any difference to me. Okay. So hopefully if you had any questions in this section, I have answered them. If you still have questions, please let me know. I did not give any homework today. What we went over today in class was really just the inequalities. And I'm going to get people to work in class tomorrow, so that homework will be posted tomorrow. So we will talk to you again soon. The test for this is going to be, oh man, it's going to be Monday. That's what we decided. It's going to be Monday. All right, bye.